You're standing outside on the coldest winter day you can remember. Your breath forms clouds in the air, your fingers ache despite your gloves, and you're counting the seconds until you can get back inside. That bone-chilling cold you're feeling. It's probably around -20 degrees Fahrenheit. Now, hold that sensation in your mind, because what I'm about to tell you will make your worst winter day feel like a tropical vacation. There are places in our solar system where the cold is so extreme, so utterly hostile to everything we know about warmth and comfort, that the very air itself would freeze solid and crash to the ground like snow. I'm talking about temperatures that would make Antarctica look like the Sahara Desert. We're heading to the outer reaches of our solar system, to two mysterious ice giants that exist in a realm of perpetual winter so severe it defies imagination. Uranus and Neptune. These aren't just distant dots of light in our telescopes. They're entire worlds, each one roughly 4 times the size of Earth, floating in the cosmic deep at distances so vast that sunlight takes hours to reach them. And when it finally does arrive, it's nothing more than a pale whisper of the warmth we feel here at home. But here's what's truly mind-blowing about this journey we're taking together. The distance to these frozen giants isn't just measured in miles or kilometers. It's measured in the fundamental limits of human comprehension. We're talking about numbers so large they break our everyday understanding of space. And the temperatures, they represent the closest thing to absolute nothingness that exists anywhere in our solar system. If you find comfort in these gentle explorations of space and science, I'd be grateful if you consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. By any chance, if your curiosity stretches beyond space and science, I would love to invite you all to visit and take a look at our new channel, Boring Money, a place where finance slows down and fortune gently drifts in. I have dropped a link in the video description. Do consider checking it out. Let's start. I'm about to take you on a journey that will challenge everything you think you know about cold and distance. By the end of this video, you'll understand not just how far these ice worlds are and how cold they get, but why those numbers reveal something profound about our place in the universe. You'll discover why NASA scientists consider these planets among the most alien places we've ever studied, and how the extreme conditions there might actually hold the key to understanding how our entire solar system formed. But first, let me set the stage with something that will blow your mind. The distance between Earth and Neptune is so enormous that if you could drive there in a car traveling at highway speeds without ever stopping, the journey would take you over 4,000 years. That's longer than all of recorded human history. And that's just the distance. The cold waiting for you at the end of that impossible journey would kill you in ways you can't imagine. So buckle up, because we're about to explore two of the most extreme environments in our solar system, and the numbers we're going to encounter will change how you think about space forever. Let me start with something that might surprise you. When most people think about the planets in our solar system, they imagine them lined up in neat rows, like they appear in textbooks. Mercury, Venus, Earth, Mars, then a big gap, and finally Jupiter, Saturn, Uranus, and Neptune stretched across the page in orderly fashion. But that textbook image completely fails to capture the mind-bending reality of just how far apart these worlds actually are. To understand the true distance to Uranus and Neptune, we need to start with something familiar. The distance from Earth to the Sun is about 93 million miles. Astronomers call this distance one astronomical unit, or AU for short. It's our cosmic yardstick, our way of measuring the vast emptiness between worlds. Light from the sun takes 8 minutes and 20 seconds to travel this distance to reach Earth. That seems pretty far, right? Well, hold on to that thought. Uranus orbits the sun at an average distance of 19 AU. That means it's 19 times farther from the sun than Earth is. In actual miles, we're talking about roughly 1.8 billion miles. But here's where it gets really interesting. Because the planets don't stay in fixed positions, the distance between Earth and Uranus is constantly changing. When Earth and Uranus are on the same side of the sun, they're about 1.7 billion miles apart. When they're on opposite sides, that distance stretches to nearly 1.98 billion miles. But Neptune exists in a realm so distant, it almost belongs to interstellar space. This ice giant orbits at an average distance of 30 AU from the sun. That's 30 times farther than Earth, or roughly 2.8 billion miles. When Earth and Neptune are closest, they're still separated by about 2.7 billion miles. At their farthest, that gap grows to over 2.9 billion miles. Now, I know these numbers are starting to feel abstract. Billions of miles don't mean much to our brains because we have no reference point for such distances. So let me put this in perspective with some comparisons that might help these cosmic distances become real. If Earth were the size of a marble, the sun would be about the size of a large beach ball located roughly 26 feet away. On this same scale, Uranus would be about the size of a golf ball, sitting nearly 500 feet away from the sun. That's 5 football fields. Neptune would be a slightly smaller golf ball positioned about 780 feet away, or roughly 2.5 football fields farther out than Uranus. But even that comparison doesn't capture the true emptiness of space. If we kept everything to scale, the nearest star beyond our sun would be located over 4,000 miles away from our marble-sized Earth. We're talking about distances that make the space between planets look crowded by comparison. Here's another way to think about it. Light, which travels at the fastest possible speed in the universe, takes about 2 hours and 40 minutes to travel from the sun to Uranus. For Neptune, that journey takes over 4 hours. This means that when you look at these planets through a telescope, you're not seeing them as they are right now. You're seeing Uranus as it was nearly 3 hours ago, and Neptune as it was over 4 hours ago. And if you think the distance is extreme, wait until you hear about the temperatures. Because when sunlight finally reaches these distant worlds, it arrives as little more than a faint echo of the warmth we experience on Earth. The amount of sunlight that reaches Uranus is only about 1/400th of what Earth receives. Imagine taking the brightness of a sunny day and dimming it by a factor of 400. At that distance from the sun, our star would appear as nothing more than a very bright star in the sky, barely larger than a pinpoint of light. For Neptune, the situation is even more extreme. This distant world receives only 1/900th of Earth's sunlight. The sun, viewed from Neptune, would be indistinguishable from a bright star. There would be no visible disk, no sense that you're orbiting around anything other than a slightly brighter point of light among thousands of others. This lack of solar energy has profound consequences for the temperatures on these worlds. And here's where we encounter cold beyond anything in human experience. The upper atmosphere of Uranus reaches 7 degrees Fahrenheit. That's temperatures of -350, only about 116 degrees above absolute zero, the theoretical temperature at which all molecular motion stops. At these temperatures, the very air we breathe would instantly freeze solid and fall to the ground like chunks of ice. But Neptune, despite being even farther from the sun, presents us with one of the most puzzling mysteries in planetary science. You might expect it to be colder than Uranus, since it receives even less sunlight. but the reality is more complex. Neptune's upper atmosphere averages around negative 330 degrees Fahrenheit. That's still unimaginably cold, but it's actually about 27 degrees warmer than Uranus. This temperature difference has baffled scientists for decades. How can a planet farther from the Sun be warmer than one closer to it? The answer lies in the internal structure of these ice giants, and it reveals something fascinating about how planets work. Unlike Earth, which gets virtually all its heat from the Sun, both Uranus and Neptune generate their own internal heat. But they do so in dramatically different ways, and this difference explains the temperature puzzle. Neptune radiates about 2.5 times more energy than it receives from the Sun. This means there's a powerful heat source deep within the planet, likely left over from its formation billions of years ago. This internal furnace helps warm Neptune's atmosphere from below, partially offsetting the extreme cold of space. Uranus, on the other hand, radiates almost no excess heat. It's essentially a cold, dead world in terms of internal energy. Scientists believe this difference might be related to a catastrophic collision that occurred early in Uranus's history. An impact so severe it knocked the planet on its side and may have disrupted its internal heat generation. The result of this internal heating difference is that while both planets are unimaginably cold by Earth standards, Neptune maintains temperatures that are slightly less hostile to existence, though still utterly lethal to any form of life we can imagine. But the extreme cold on these worlds creates phenomena that don't exist anywhere else in our solar system. The atmospheric pressure and temperature conditions on both planets allow for the formation of exotic forms of ice that can't exist on Earth. We're talking about ice made not just from water, but from methane, ammonia, and hydrogen sulfide. These substances, which are gases at Earth temperatures, become solid crystals in the frigid atmospheres of the ice giants. The clouds on these worlds are made of materials that would seem alien to us. Methane ice crystals float through atmospheres of hydrogen and helium, creating weather systems unlike anything on Earth. On Neptune, winds reach speeds of over 1,000 miles per hour, making them the fastest recorded winds in the solar system. Imagine hurricane-force winds that never stop, carrying ice crystals through an atmosphere so no would be frozen solid. They represent real places, actual worlds, where the laws of physics play out under conditions so extreme they challenge our understanding of what's possible. And we're just getting started, because the journey to understand these distant ice giants reveals something profound about the nature of our solar system and our place within it. The distances we've discussed, the temperatures we've explored, they're all part of a larger story about how planets form, how solar systems evolve, and what makes Earth so remarkably special in this cosmic context. The extreme conditions on these ice giants become even more fascinating when we consider what lies beneath their frozen atmospheres. While the surfaces of these worlds are hostile beyond imagination, the interiors tell a story of pressure and heat that defies everything we think we know about cold planets. Beneath the swirling clouds of methane and ammonia ice, both Uranus and Neptune hide secrets that would revolutionize our understanding of planetary formation if we could somehow journey there. The pressure deep within these worlds is so intense that it transforms ordinary materials into substances that shouldn't exist according to our everyday experience of physics. Imagine descending through the atmosphere of Neptune. As you fall deeper and deeper through layers of increasingly dense gas, the pressure around you builds to levels that would crush any spacecraft we've ever built. At depths of just a few hundred miles, the pressure becomes so extreme normally a gas transforms into a solid form of ice unlike anything on Earth. But this isn't the familiar ice you find in your freezer. This is hot ice. maintaining its solid structure despite temperatures that would melt steel. Continue deeper, and the conditions become even more extraordinary. Scientists believe that at the cores of both Uranus and Neptune, pressures reach millions of times greater than what we experience at Earth's surface. Under these crushing conditions, water molecules are squeezed so tightly together that they form superionic ice, a bizarre state of matter where oxygen atoms are locked in a crystalline structure, while hydrogen atoms flow freely through the crystal like a liquid. But here's where the story becomes even more mind-bending. Some scientists theorize that the cores of these planets might contain oceans of liquid diamond. Yes, you heard that correctly. Diamond oceans. Under the extreme pressures and temperatures deep within Uranus and Neptune, carbon atoms are compressed into diamond structures, but the conditions are so intense that these diamonds exist in a liquid state. Picture an ocean deeper than any on Earth, filled not with water, but with flowing liquid diamond, existing under pressures that would instantly crush anything from our world. These aren't just theoretical curiosities. The exotic forms of matter that exist within these ice giants might hold the key to understanding how our entire solar system formed. The composition and structure of Uranus and Neptune provide clues about the early solar system, when planets were still forming from the disk of dust and gas that surrounded our young sun. Current theories suggest that these ice giants didn't form where they are today. Instead, they likely formed much closer to the sun, in the region where Jupiter and Saturn now orbit, before being gravitationally scattered outward to their current frozen positions. This migration theory explains why Uranus and Neptune are so different from the gas giants Jupiter and Saturn, despite being in the same outer region of our solar system. The evidence for this planetary migration lies partly in the unusual properties of these worlds that we've been discussing. The fact that Neptune generates more internal heat than Uranus, despite being farther from the Sun, suggests different formation histories. Neptune may have retained more of its original heat from formation because it migrated outward more recently, while Uranus may have been in its current position longer, giving it more time to cool down. This migration also explains why the outer solar system contains so much empty space. When Jupiter, Saturn, Uranus, and Neptune moved to their current positions, their gravitational influence scattered countless smaller objects throughout the outer solar system, creating the Kuiper Belt and the even more distant Oort cloud. But the story becomes even more remarkable when we consider the moons that orbit these distant worlds. Because despite the extreme cold and the vast distances from the Sun, both Uranus and Neptune host families of moons that might harbor some of the most interesting chemistry in our solar system. Neptune's largest moon, Triton, is one of the most geologically active objects we know of in the outer solar system. Despite receiving virtually no heat from the Sun at Neptune's distance, Triton shows signs of nitrogen geysers erupting from its surface. These geysers suggest that some internal heat source is driving geological activity on a world that should be completely frozen and dead. The temperature on Triton's surface averages around -390 degrees Fahrenheit, making it one of the coldest places we've measured in our solar system. Yet this frozen world somehow maintains enough internal energy to drive active geology. The nitrogen geysers shoot material up to 5 miles high in Triton's thin atmosphere, creating dark streaks across the moon's icy surface that we can observe from billions of miles away. Uranus has its own collection of fascinating moons, though they're less well understood because we've only visited the Uranus system once, during Voyager 2's flyby in 1986. The largest of Uranus's moons, Titania, shows evidence of past geological activity, despite the extreme cold at Uranus's distance from the Sun. Massive canyons scar Titania's surface, suggesting that internal forces once shaped this distant world. These moons represent some of the most extreme environments we know of, places where the cold is so intense that familiar substances behave in completely alien ways. On these worlds, nitrogen, which makes up most of Earth's atmosphere, exists as ice. Methane, a gas at Earth temperatures, forms vast frozen deposits. Water ice, instead of melting, can exist in multiple exotic crystalline forms that don't occur naturally anywhere on Earth. The radiation environment around these distant worlds adds another layer of hostility. Both Uranus and Neptune have magnetic fields that trap charged particles from the solar wind, creating radiation belts similar to Earth's Van Allen belts, but far more intense. Any spacecraft visiting these systems must be designed to withstand radiation levels that would quickly destroy unprotected electronics. Yet, despite all these hostile conditions, or perhaps because of them, these ice giants represent some of the most scientifically valuable targets in our solar system. Every extreme condition we've discussed, from the crushing pressures to the exotic forms of ice to the mysterious internal heat sources, provides a window into physical processes that we can't study anywhere else. The magnetic fields of these planets, for example, are completely unlike anything we see in the inner solar system. Uranus's magnetic field is tilted at nearly 90 degrees relative to its rotation axis, while Neptune's magnetic field is offset from the planet's center by about half a planetary radius. These unusual magnetic field configurations challenge our understanding of how planetary magnetic fields are generated and maintained. Understanding these magnetic field anomalies isn't just academic curiosity. Magnetic fields play crucial roles in protecting planetary atmospheres from being stripped away by the solar wind. The unusual magnetic fields of Uranus and Neptune might explain why these planets have retained their thick atmospheres despite billions of years of exposure to space weather. This brings us to one of the most profound questions these ice giants pose. Could life exist under such extreme conditions? While the surface temperatures we've discussed would instantly kill any known form of life, the deep interiors of these worlds might tell a different story. The superionic ice and liquid diamond oceans we discussed earlier exist at temperatures and pressures that, be automatically while extreme, might not hostile to certain forms of chemistry. Some scientists speculate that the boundary layers between different phases of matter deep within these planets could harbor chemical processes unlike anything we see on Earth. These aren't the familiar biochemical processes that support life as we know it, but rather exotic chemical systems that might operate under the extreme conditions found deep within ice giants. The flowing hydrogen atoms in superionic ice, for example, might enable chemical reactions that are impossible under normal conditions. While we're nowhere near being able to investigate such possibilities directly, the mere fact that we can conceive of them illustrates how much these distant, frozen worlds continue to challenge and expand our understanding of what's possible in the universe. The distances that separate us from these ice giants, those billions of miles we discussed, represent more than just measurements of space. They represent the frontier of human knowledge, the boundary between what we can study directly and what we can only investigate through the faint signals that reach us across the cosmic void. Every piece of data we collect from these distant worlds represents a triumph of human ingenuity over impossible odds. The spacecraft that have visited these realms had to be engineered to survive journeys lasting decades, operating in conditions that would destroy most technology within minutes. When Voyager 2 flew past Uranus in 1986, it was humanity's first and only close encounter with this tilted ice giant. The spacecraft had been traveling for nearly 9 years just to reach Uranus, and the data it collected during its brief flyby continues to shape our understanding today. That flyby revealed Uranus to be even stranger than anyone had imagined. Not only does this world orbit on its side, with its north and south poles pointing toward and away from the Sun during different parts of its 84-year orbit, but its entire system of moons and rings is tilted along with it. Picture a planet where summer and winter each last 42 Earth years, where one hemisphere experiences continuous daylight for decades, while the other endures an equally long polar night. This extreme seasonal cycle creates weather patterns unlike anything else in our solar system. During Uranus's long summers and winters, temperature differences between the day and night sides of the planet become so extreme that they drive atmospheric circulation patterns spanning entire hemispheres. Winds carry heat from the perpetually sunlit summer pole toward the frozen winter pole, creating global weather systems that persist for decades at a time. But here's what makes this even more extraordinary. Despite these extreme seasonal variations, Uranus maintains remarkably uniform temperatures across its entire surface. The planet's equatorial regions, which receive more consistent sunlight throughout its orbit, are nearly the same temperature as its polar regions. This temperature uniformity suggests that Uranus has some mechanism for distributing heat that we don't fully understand. Another mystery to add to the growing list surrounding this enigmatic world. Neptune's weather systems present their own set of mind-bending phenomena. Remember those 1,000-mile-per-hour winds I mentioned earlier? These aren't temporary storm systems like hurricanes on Earth. They're permanent features of Neptune's atmosphere, jet streams of frozen methane and hydrogen that have been raging for as long as we've been able to observe them. The Great Dark Spot, Neptune's equivalent to Jupiter's Great Red Spot, was first observed by Voyager 2 in 1989. This massive storm system was roughly the size of Earth, with winds circulating at speeds that would make a Category 5 hurricane look like a gentle breeze. But when the Hubble Space Telescope turned its gaze toward Neptune in the 1990s, the Great Dark Spot had vanished, replaced by new storm systems in different parts of the planet's atmosphere. This rapid change in Neptune's weather patterns tells us something crucial about the dynamics of these distant worlds. Unlike the stable, long-lived storm systems we see on Jupiter and Saturn, the weather on Neptune appears to be driven by internal heat sources that create rapid, violent changes in atmospheric circulation. The planet's internal engine, that mysterious heat source generating 2.5 times more energy than Neptune receives from the Sun, drives weather systems more dynamic than anything we see elsewhere in the outer solar system. These observations force us to confront a humbling reality about our place in the universe. From our perspective on Earth, nestled close to the Sun in the warm inner solar system, these ice giants exist in a realm so foreign, so utterly alien, that they might as well be planets orbiting other stars. The conditions we've described, the temperatures, the pressures, the exotic chemistry, represent environments that challenge every assumption we make about how planets work. Yet these worlds are our neighbors. They formed from the same disk of dust and gas that created Earth. They're governed by the same laws of physics that operate in our daily lives. The water molecules in supersonic ice deep within Neptune follow the same quantum mechanical rules as the water in your morning coffee. The difference lies only in the extreme conditions under which those rules play out. This realization leads us to one of the most profound questions in planetary science. If worlds as alien as Uranus and Neptune can exist in our own solar system, what does this tell us about the potential diversity of planets orbiting other stars? The thousands of exoplanets we've discovered in recent years include many that appear similar in size and composition to our ice giants. Are those distant worlds equally strange? Do they harbour their own forms of exotic ice and liquid diamond oceans? The answer to these questions will reshape our understanding of planetary formation and evolution. The ice giants in our solar system represent a class of planets that appears to be common throughout the galaxy. By studying Uranus and Neptune, we're learning about processes that might be playing out around countless other stars, creating worlds with conditions we can barely imagine. But studying these distant realms requires us to push the boundaries of technology and human ingenuity to their absolute limits. The signals we receive from spacecraft at these distances are so weak that detecting them requires some of the most sensitive instruments ever built. When Voyager 2 transmitted data from Neptune, the radio signals took over 4 hours to reach Earth, and they arrived with less power than a snowflake hitting the ground. The Deep Space Network, NASA's collection of massive radio telescopes scattered around the globe, represents one of humanity's greatest technological achievements, precisely because it allows us to maintain contact with spacecraft at these impossible distances. These enormous dishes, some larger than football fields, can detect signals so faint that they wouldn't power a digital watch, yet they carry within them detailed information about worlds billions of miles away. The engineering challenges of reaching these distant realms go far beyond just communication. Spacecraft traveling to the outer solar system must carry their own power sources because solar panels become useless at such vast distances from the sun. The radioisotope thermoelectric generators that powered Voyager 2's journey to Neptune use the heat from radioactive decay to generate electricity, providing steady power for decades of operation in the cold vacuum of space. These nuclear power sources aren't just technological marvels. They're time machines that allow us to extend human presence across temporal scales that dwarf individual lifetimes. Voyager 2 launched in 1977, when the personal computer was still a novelty and the internet didn't exist. Yet this spacecraft continues to transmit data today, having survived longer than many of the engineers who built it. The longevity required for missions to the outer solar system forces us to think about exploration in generational terms. Future missions to study Uranus and Neptune in detail will require commitments spanning decades, with spacecraft that won't reach their destinations until today's children are adults. The scientists who analyze the data from these missions may not even be born yet when the spacecraft launch. This temporal scale of exploration reveals something profound about human curiosity and our drive to understand the universe. We commit resources and lifetimes to studying worlds so distant and alien that they offer no immediate practical benefit to our daily lives. Yet we do it anyway, driven by the same curiosity that has pushed our species to explore every corner of our own planet and now reaches toward the stars. The extreme distances and hostile conditions we've explored in this journey to the ice giants serve as a reminder of both our limitations and our potential. We are creatures adapted for a narrow range of temperature, pressure, and radiation conditions. Yet through our technology and our mathematics, we can extend our senses to realms that would instantly destroy us. The numbers we've discussed, those billions of miles and hundreds of degrees below zero, aren't just abstract measurements. They represent the expansion of human consciousness beyond the boundaries of direct experience. When we measure the temperature of Neptune's atmosphere or calculate the pressure at Uranus's core, we're engaging in an act of intellectual courage that connects us to something larger than ourselves. These ice giants, floating in their perpetual winter at the edge of our solar system, serve as beacons of mystery that continue to draw us outward. Each new discovery about their exotic chemistry, their unusual magnetic fields, their mysterious heat sources, opens new questions that demand answers. They remind us that no matter how much we learn about the universe, there will always be new frontiers waiting to challenge our understanding. As we stand on the threshold of truly comprehending these distant worlds, we encounter something that pushes the boundaries of not just science, but imagination itself. The journey to understand what lies within these ice giants takes us into realms where the familiar rules of matter and energy break down completely, where the very concepts of hot and cold become meaningless in the face of conditions so extreme they redefine what we think is possible. Let me paint a picture that will fundamentally change how you think about temperature. Deep within Neptune, at pressures millions of times greater than anything on Earth's surface, there exists a form of water that simultaneously challenges every assumption you've ever made about the states of matter. This isn't just hot ice or cold liquid. This is something entirely different, a state of matter where water molecules exist in a crystalline structure, while their hydrogen atoms flow like a river through the crystal lattice. Scientists call this superionic water, and it exists at temperatures exceeding 4,000 degrees Fahrenheit, while remaining in what we would technically classify as a solid state. Picture holding a piece of ice that's hotter than molten steel, yet maintains its structural integrity due to the crushing pressure surrounding it. This isn't science fiction. This is the reality deep within the worlds we've been exploring. But the story becomes even more extraordinary when we consider what this means for our understanding of these planets' evolution. The superionic water and other exotic states of matter within Uranus and Neptune aren't just curiosities. They're the engines that drive these worlds' magnetic fields, their internal heat generation, and possibly even their unusual atmospheric dynamics. The magnetic field of Uranus, tilted at that impossible 90-degree angle, might be generated by layers of superionic water conducting electricity deep within the planet's interior. These conducting layers create electrical currents that, in turn, generate magnetic fields oriented in directions that seem to defy logic when viewed from our Earth-centered perspective. Neptune's offset magnetic field, displaced from the planet's center by thousands of miles, suggests an even more complex internal structure. The magnetic field generation might be occurring in multiple layers within the planet, each layer of exotic matter contributing its own magnetic signature to create the chaotic, multipolar magnetic field we observe. These magnetic field anomalies have consequences that extend far beyond the planets themselves. The interaction between these unusual magnetic fields and the solar wind creates auroras unlike anything we see on Earth. On Neptune, auroras might occur at multiple latitudes simultaneously, painting the planet's polar regions with curtains of light generated by different layers of the magnetic field interacting with charged particles from space. But here's where the temperature story becomes truly mind-bending. While we've focused on the extreme cold of these worlds' atmospheres, the internal temperatures tell a completely different story. The core of Neptune might reach temperatures of 7,000 degrees Fahrenheit, hotter than the surface of the sun. This internal furnace, burning without fuel in the heart of an ice giant billions of miles from any significant heat source, represents one of the most profound mysteries in planetary science. How does a world so far from the sun maintain internal temperatures that exceed those found in the inner solar system? The answer lies in the violent history of planetary formation, a story written in the exotic matter that makes up these worlds' interiors. When Neptune formed, gravitational collapse released enormous amounts of energy, heating the planet's interior to temperatures that would vaporize rock. But unlike smaller worlds that quickly radiated this heat away to space, Neptune's massive size and insulating atmosphere have allowed it to retain much of that primordial heat for over 4 billion years. The result is a world where the temperature difference between the surface and the core spans a range that encompasses nearly every extreme condition found anywhere in our solar system. From the negative 330 degrees of the upper atmosphere to the 7,000-degree inferno at the core, Neptune contains within its structure a complete spectrum of thermal environments. This temperature gradient creates convection currents within the planet's interior that dwarf anything we see on Earth. Imagine columns of superionic water and liquid diamond rising and falling through the planet's interior, carrying heat from the core toward the surface in convection cells thousands of miles tall. These internal circulation patterns might be what drives Neptune's extreme weather systems, feeding energy from the planet's hot interior into atmospheric dynamics that create the fastest winds in the solar system. The implications of this internal heat transport extend to questions about the planet's long-term evolution. While Earth's internal heat comes primarily from radioactive decay, Neptune's heat source appears to be primarily gravitational, left over from the planet's formation. This means Neptune is slowly cooling over geological time, gradually radiating away the energy that has kept its interior molten for billions of years. But the cooling process isn't uniform. Different layers within the planet cool at different rates, creating thermal instabilities that might periodically reorganize the planet's entire internal structure. These reorganization events could explain the rapid changes we observe in Neptune's atmospheric weather patterns, as shifts in internal heat transport suddenly alter the energy flow from the planet's interior to its atmosphere. Uranus presents an even more puzzling thermal story. Despite being closer to the Sun than Neptune, Uranus radiates almost no excess heat to space. This suggests that something in Uranus's history disrupted its internal heat engine, leaving it as a cold, nearly dead world in terms of internal energy. The leading theory involves a catastrophic collision early in Uranus's history. Computer simulations suggest that an impact with an Earth-sized object could have knocked Uranus on its side, while simultaneously disrupting the convection patterns that normally transport heat from a planet's core to its surface. The result would be a world where internal heat becomes trapped in the deep interior, unable to reach the surface and radiate away to space. This trapped heat might still exist deep within Uranus, locked away beneath layers of superionic ice and other exotic materials that act as thermal insulators. If this theory is correct, then Uranus's interior might be nearly as hot as Neptune's, but the heat simply can't escape to warm the planet's atmosphere and surface. The possibility of trapped heat within Uranus opens fascinating questions about the planet's future evolution. If geological processes or internal instabilities eventually allowed this trapped heat to escape, Uranus could undergo a dramatic transformation, developing internal heat transport and atmospheric dynamics similar to Neptune's. The planet might literally wake up from its current dormant state, developing weather systems and magnetic field configurations that are completely different from what we observe today. These thermal mysteries extend to the moons orbiting these ice giants, creating environments that challenge our understanding of what's possible in the outer solar system. Triton, Neptune's largest moon, shows clear evidence of geological activity despite receiving virtually no heat from the Sun at Neptune's distance. The nitrogen geysers we discussed earlier require internal heat sources that shouldn't exist on such a small, distant world. The most likely explanation involves tidal heating generated by Triton's interaction with Neptune's gravity. As Triton orbits Neptune, gravitational forces flex and distort the moon's interior, generating heat through friction in the same way that repeatedly bending a wire makes it warm to the touch. But the amount of tidal heating required to drive Triton's geological activity suggests that this moon's interior might be far more dynamic than we previously imagined. Triton's retrograde orbit, moving in the opposite direction from Neptune's rotation, provides clues about its origin and thermal history. This backward orbit suggests that Triton is a captured Kuiper Belt object, a dwarf planet similar to Pluto that was gravitationally captured by Neptune sometime in the distant past. The capture process would have been violent, involving orbital changes that generated enormous amounts of tidal heating. This heating might have temporarily melted Triton's interior, creating a subsurface ocean that could persist for millions or even billions of years beneath the moon's frozen surface. If such an ocean exists, it would represent one of the most isolated bodies of liquid water in our solar system, a hidden sea existing in perpetual darkness, billions of miles from the sun. The chemistry of such an ocean would be unlike anything on Earth. With no input of solar energy and minimal heat from radioactive decay, any chemical processes would have to derive energy from the interaction between liquid water and the rocky materials in Triton's interior. These are the same types of chemical processes that might have given rise to life on Earth, operating in environments where sunlight never penetrates. The moons of Uranus present their own thermal mysteries. These worlds show evidence of past geological activity despite existing in one of the coldest environments in our solar system. The large moon Titania displays massive canyon systems that could only have formed if the moon's interior was once warm enough to allow expansion and contraction of subsurface materials. The source of this ancient heat remains unclear. Unlike Triton, Uranus's moons all orbit in the same direction as their planet's rotation, suggesting they formed in place rather than being captured from elsewhere. But their small sizes should have allowed any primordial heat to radiate away to space within a few 100 million years of formation. One possibility involves the same catastrophic impact that tilted Uranus on its side. Such a collision would have released enormous amounts of energy throughout the Uranian system, temporarily heating the planet's moons to temperatures that could drive geological activity. The canyon systems we observe on Titania and other Uranian moons might be fossil remnants of this ancient heating event, preserved in the deep freeze of the outer solar system like snapshots of a more dynamic past. These thermal histories of the ice giants and their moons illustrate a fundamental principle of planetary science that extends far beyond our solar system. The conditions we observe today on any world represent only a single moment in a billions-year-long story of thermal evolution. The extreme cold we measure in the atmospheres of Uranus and Neptune tells us about current conditions, but it doesn't reveal the complex thermal processes operating deep within these worlds, or the dramatic changes they've undergone throughout their histories. This temporal perspective becomes crucial when we consider the search for life in our solar system and beyond. The subsurface oceans that might exist within the moons of these ice giants wouldn't be detectable through atmospheric observations. They represent hidden biospheres that could persist for billions of years in environments that appear completely sterile from the outside. The techniques we're developing to study these hidden thermal processes will become essential tools for characterizing potentially habitable worlds orbiting other stars. Many of the exoplanets we've discovered appear similar in size and composition to Uranus and Neptune, and they likely harbor the same types of exotic internal chemistry and hidden thermal dynamics we've been exploring. Understanding how heat flows through the interiors of ice giants, how exotic states of matter form and evolve under extreme conditions, and how these processes influence surface and atmospheric conditions will help us interpret observations of distant worlds that we can study only through the faint signals of their starlight. The extreme distances we discussed at the beginning of our journey, those billions of miles that separate us from these ice giants, represent more than just measurements of space. They represent the frontiers of human knowledge, the boundaries between what we can study directly and what we can only investigate through the mathematical models and physical theories that extend our understanding beyond the reach of direct observation. Every number we've discussed, every temperature measurement and pressure calculation, represents a triumph of human reasoning over impossible odds. When we determine that superionic water exists in Neptune's interior, we're not just making an academic observation, we're extending human consciousness into realms that no direct experience could ever reach, using the power of scientific reasoning to explore conditions that would instantly destroy any conceivable probe or instrument. This intellectual journey to the hearts of distant worlds reveals something profound about the nature of scientific discovery itself. The most important truths about the universe often lie hidden in the most extreme environments, the places that push the boundaries of what's physically possible. The ice giants, with their exotic chemistry and extreme thermal gradients, serve as natural laboratories for studying physics under conditions that we could never recreate on Earth. The knowledge we gain from studying these distant worlds doesn't just satisfy our curiosity about the solar system. It provides crucial insights into the fundamental behavior of matter and energy under extreme conditions, insights that inform everything from materials science to fusion energy research. The superionic water that exists deep within Neptune might someday inspire new technologies for energy storage or materials engineering, applications that emerge from our exploration of the most alien environments in our cosmic neighborhood. As we prepare to delve even deeper into the mysteries of these ice giants, remember that we've only begun to scratch the surface of what makes these worlds so extraordinary. The distances and temperatures we've explored represent just the beginning of a story that encompasses the formation of our entire solar system, the potential for life in the most unlikely places, and the ongoing evolution of worlds that continue to surprise us with their complexity and beauty. The journey ahead will take us into even more mind-bending territory, where the very concepts of distance and temperature will be challenged by phenomena that exist nowhere else in human experience. We're about to discover how these extreme worlds might hold the keys to understanding not just our own solar system, but the countless other planetary systems that populate our galaxy. The story of how we came to understand these impossible distances and temperatures is itself a testament to human ingenuity that spans centuries. When William Herschel first spotted Uranus through his telescope in 1781, he thought he was looking at a comet. The idea that there could be worlds so distant, so fundamentally different from anything in human experience, was beyond the imagination of even the most visionary astronomers of his time. Herschel's discovery doubled the known size of our solar system overnight. Suddenly, the cosmic neighborhood that had seemed so well mapped and understood revealed itself to be far vaster and more mysterious than anyone had dared to imagine. But it would be another 65 years before Neptune's existence was even suspected, and its discovery represents one of the most remarkable detective stories in the history of science. By the mid-1800s, astronomers had been tracking Uranus for decades, and something was wrong. The planet wasn't following the orbital path that Newton's laws of gravity predicted it should. Instead of moving in a perfect ellipse around the sun, Uranus seemed to be speeding up and slowing down in ways that made no sense according to the established laws of physics. Two mathematicians, working independently on opposite sides of the English Channel, proposed a solution so bold it seemed almost absurd. Urbain Le Verrier in France and John Couch Adams in England suggested that the gravitational pull of an undiscovered planet was tugging on Uranus, causing the orbital irregularities astronomers had observed. Using nothing but mathematical calculations based on Uranus's orbital deviations, Leverrier predicted exactly where in the sky this hypothetical planet should be located. When German astronomer Johann Galle pointed his telescope toward Leverrier's predicted coordinates on September 23, 1846, he found Neptune within 1 degree of the calculated position. Think about what this represents. These mathematicians had used the subtle gravitational influence of an invisible world to predict the existence and location of a planet nearly 3 billion miles away. They had discovered Neptune with pencil and paper before anyone had ever seen it through a telescope. It was a triumph of mathematical reasoning that proved the universal nature of physical laws across distances that dwarfed human comprehension. But even as astronomers celebrated this mathematical tour de force, they had no idea just how alien the world they had discovered truly was. The temperatures and conditions we've been exploring were completely beyond the scientific understanding of the 19th century. The concept of absolute zero wouldn't be developed until the 1840s, and the exotic states of matter that exist within these ice giants weren't even theoretical possibilities in the minds of Victorian-era scientists. The first hints of just how strange these distant worlds might be came from spectroscopic analysis in the early 20th century. By analyzing the light reflected from Uranus and Neptune, astronomers discovered that both planets absorbed specific wavelengths of red light, giving them their distinctive blue-green and deep blue colors respectively. This absorption was caused by methane in their atmospheres, the first indication that these worlds contained chemistry unlike anything found on the inner planets. But it wasn't until the space age that we began to grasp the true extremes of temperature and pressure that characterize these distant realms. The Voyager missions, launched in the 1970s, represented humanity's first serious attempt to explore the outer solar system in detail. These spacecraft had to be engineered to survive journeys lasting decades through environments that would destroy conventional electronics within hours. The engineering challenges of reaching these distant worlds pushed 1970s technology to its absolute limits. Voyager 2's encounter with Uranus in 1986 required the spacecraft to operate flawlessly after nearly a decade of travel through the radiation-filled void between planets. By the time it reached Uranus, many of its backup systems had already failed, yet it continued to function well enough to revolutionize our understanding of this tilted ice giant. The data Voyager 2 transmitted back to Earth revealed a world even stranger than anyone had predicted. Not only was Uranus rotating on its side, but its entire system of moons and rings was tilted along with it, creating a planetary system unlike anything else in our solar system. The magnetic field measurements showed that chaotic, multipolar structure we discussed earlier, hinting at exotic processes occurring deep within the planet's interior. When Voyager 2 continued on to Neptune in 1989, it encountered weather systems so violent they challenged our understanding of atmospheric dynamics. The Great Dark Spot, larger than Earth and driven by winds exceeding the speed of sound, demonstrated that these frigid worlds could generate more dynamic weather than planets much closer to the sun's warming influence. The temperature measurements from both encounters provided the first direct evidence of the extreme thermal conditions we've been exploring. When Voyager 2's instruments detected that Neptune was actually warmer than Uranus despite being farther from the Sun, it opened up entirely new questions about planetary heat sources and internal dynamics. These discoveries transformed our understanding of what planetary science meant in the context of the outer solar system. The familiar models of planetary behavior, developed through centuries of studying the inner planets, simply didn't apply to these exotic ice giants. New theoretical frameworks had to be developed to explain how worlds could maintain complex atmospheric dynamics at temperatures that would freeze most known substances solid. The exotic chemistry occurring within these planets pushes the boundaries of materials science in ways that continue to surprise researchers today. Laboratory experiments attempting to recreate the conditions deep within Uranus and Neptune require some of the most extreme pressure and temperature facilities on Earth, yet they can only approximate a tiny fraction of the conditions that exist naturally within these distant worlds. Recent experiments using diamond anvil cells, devices that can generate pressures exceeding those found at Earth's core, have begun to recreate some of the exotic states of matter we believe exist within ice giants. These experiments have confirmed the existence of supersonic ice at pressures and temperatures that seemed impossible just decades ago, validating theoretical predictions about the internal structure of these distant worlds. But perhaps the most remarkable aspect of these laboratory investigations is what they reveal about the universality of physical processes. The same quantum mechanical principles that govern the behavior of atoms in your morning coffee also determine how matter behaves under the crushing pressures deep within Neptune. The difference lies only in the extreme conditions under which these principles operate. This universality extends to the formation processes that created these worlds billions of years ago. The gravitational collapse that generated the internal heat still warming Neptune's core follows the same physical laws that govern star formation in distant galaxies. The tidal forces that might be heating Triton's interior operate according to the same principles that create ocean tides here on Earth, scaled up to planetary dimensions. Understanding these connections between familiar physics and extreme environments has profound implications for our interpretation of observations from other star systems. The thousands of exoplanets discovered by space telescopes like Kepler and TESS include many worlds similar in size and mass to Uranus and Neptune. These distant ice giants likely harbor the same types of exotic chemistry and complex thermal dynamics we've been exploring in our own solar system. Current missions being planned by space agencies around the world will push our exploration of these extreme environments even further. Proposed orbital missions to both Uranus and Neptune would carry instruments capable of peering deep into these planets' interiors, using gravitational measurements and magnetic field mapping techniques that didn't exist during the Voyager era. These future missions face engineering challenges that dwarf even the impressive achievements of Voyager 2. Spacecraft designed to orbit these distant worlds must carry enough fuel to operate for decades in the outer solar system, while maintaining precise orbital trajectories around planets whose gravitational fields are still not completely understood. The communication delays we discussed earlier create additional complications for mission planning. Commands sent to a spacecraft orbiting Neptune take over 4 hours to arrive, making real-time control impossible. These future explorers will need to operate with levels of autonomy that push the boundaries of current artificial intelligence technology, but the scientific rewards of such missions would be extraordinary. Detailed gravitational mapping could reveal the exact structure of these planets' interiors, confirming or refuting our theories about supersonic ice and liquid diamond oceans. Atmospheric probes could directly sample the exotic chemistry occurring in these worlds' deep atmospheres, providing ground truth for our understanding of how matter behaves under extreme conditions. Long-term orbital observations would allow us to monitor the seasonal changes on these worlds as they progress through their decades-long years. For Uranus, this means watching how a planet responds as its poles gradually shift from pointing directly at the sun to pointing perpendicular to it. A thermal experiment playing out on planetary scales over human lifetimes. The magnetic field measurements from such missions could solve the puzzle of these planets' unusual magnetic geometries, potentially revealing new mechanisms for magnetic field generation that don't operate anywhere else in our solar system. Understanding these mechanisms could have applications for plasma physics research and fusion energy development here on Earth. Perhaps most intriguingly, detailed studies of the moons orbiting these ice giants could reveal whether the subsurface oceans we've theorized actually exist. If confirmed, these hidden seas would represent some of the most isolated and exotic aquatic environments in our solar system, potentially harboring chemistry and even biology, unlike anything found on Earth. The search for life in these unlikely environments would require entirely new approaches to astrobiology. The chemical processes that might support life in the subsurface oceans of ice giant moons would operate without any input of solar energy, deriving all their power from the interaction between liquid water and rocky materials in the moon's interiors. These are the same types of chemosynthetic processes that support life around deep-sea hydrothermal vents on Earth, but operating under conditions of extreme isolation that would make Earth's deepest ocean trenches seem accessible by comparison. Any life that might exist in such environments would represent a completely independent genesis of biology, evolved in isolation from the sun-powered biosphere that characterizes life as we know it. The implications of discovering such life would extend far beyond biology to questions about the prevalence of life throughout the universe. If life can arise and persist in the subsurface oceans of ice giant moons, then similar environments around other stars might harbor their own unique forms of biology. The number of potentially habitable worlds in our galaxy could be orders of magnitude larger than current estimates based on planets orbiting within their stars' habitable zones. These possibilities transform our understanding of what it means for a world to be habitable. The traditional concept of a habitable zone, that narrow range of distances from a star where liquid water can exist on a planet's surface, becomes almost irrelevant when considering the potential for subsurface oceans heated by internal energy sources. The ice giants we've been exploring, with their exotic internal chemistry and complex thermal dynamics, represent natural laboratories for studying the conditions that might support life throughout the galaxy. The extreme environments within these worlds and their moons provide insights into the boundaries of what's possible for biology under conditions that exist nowhere else in our direct experience. As we continue to push the boundaries of our exploration of these distant realms, we encounter phenomena that challenge not just our scientific understanding, but our fundamental concepts of what constitutes a world. The exotic states of matter, the extreme temperature gradients, the unusual magnetic field configurations all point toward a universe far stranger and more diverse than our Earth-centered perspective might suggest. The journey to understand these ice giants has taken us from the mathematical predictions of 19th century astronomers to the cutting-edge laboratory experiments attempting to recreate the conditions in planetary interiors. Each step in this journey has revealed new mysteries while solving others, creating an ever-expanding frontier of questions about the nature of worlds and the processes that shape them. The distances and temperatures we've explored represent more than just extreme measurements. They represent the expansion of human consciousness beyond the comfortable boundaries of direct experience into realms where only mathematics and scientific reasoning can guide our understanding. In pushing ourselves to comprehend these alien environments, we develop new ways of thinking about the universe and our place within it. The story of these ice giants continues to evolve as new observations and theoretical insights reshape our understanding of what these worlds represent. Each new measurement of their atmospheric composition, each refinement of our models of their internal structure, each discovery about their magnetic fields, and thermal dynamics adds another piece to a puzzle that may take generations to complete. Yet even as we work to solve these puzzles, we can appreciate the profound beauty of worlds that exist at the very edge of what's possible within the laws of physics. The ice giants, floating in their perpetual winter billions of miles from the sun, serve as reminders that the universe contains wonders beyond our wildest imagination, challenges that will continue to drive human curiosity and ingenuity for centuries to come. The extreme conditions we've explored, from the crushing pressures that create liquid diamond oceans to the temperatures that simultaneously freeze and burn, represent the universe testing the limits of its own physical laws. In studying these extreme environments, we learn not just about distant worlds, but about the fundamental nature of matter, energy, and the forces that shape reality itself. These lessons extend far beyond planetary science to questions about the evolution of the universe, the formation of solar systems, and the potential for life in environments we're only beginning to understand. The ice giants, in all their alien majesty, continue to teach us that the cosmos is far stranger, far more wonderful, and far more full of possibilities than we ever dared to imagine. As we stand at the threshold of truly understanding what it means to exist in the outer reaches of our solar system, we encounter something that fundamentally challenges our perception of planetary death and rebirth. Because while we've explored the crushing, cold, and impossible distances, there's a hidden story playing out within these ice giants that reveals the universe's capacity for transformation on scales that dwarf human comprehension. Deep within the cores of both Uranus and Neptune, pressures reach levels so extreme that they literally reshape the architecture of matter itself. We're not just talking about crushing force, we're talking about conditions where the familiar rules of chemistry cease to apply, where atoms are compressed into configurations that exist nowhere else in our solar system. At the heart of Neptune, pressures exceed 3 million times what you experience at sea level. Under these conditions, carbon atoms don't just form diamonds, they create a form of crystalline structure so dense, so perfectly organized, that it represents matter in a state we can barely comprehend. These aren't the diamonds you might find in jewelry. These are atomic arrangements where every carbon atom is locked into a crystal lattice under such tremendous force that the resulting material would be harder than anything that exists on Earth's surface. But here's where the story becomes truly extraordinary. At the temperatures and pressures deep within these ice giants, these supercompressed diamonds don't remain solid. The thermal energy is so intense that these impossibly hard materials exist in a liquid state, creating oceans of flowing diamond that stretch for thousands of miles through the planet's interiors. Picture this for a moment. An ocean deeper than any on Earth, filled not with water but with liquid carbon in its most compressed crystalline form. These diamond seas exist at temperatures that would vaporize steel, yet remain liquid due to the crushing gravitational forces pressing down from above. It's an environment where our most basic understanding of solid and liquid breaks down completely. The chemical processes occurring in these diamond oceans drive phenomena that extend throughout these worlds' entire structure. The flow of liquid diamond creates convection currents that transport heat from the planet's cores toward their surfaces, influencing everything from magnetic field generation to atmospheric dynamics. These internal diamond rivers might be what powers Neptune's extraordinary weather systems, feeding energy from the planet's molten heart into atmospheric circulation patterns that create the fastest winds in our solar system. Recent computer simulations suggest that these liquid diamond oceans aren't uniform. Instead, they form layers, each with different densities and compositions, creating a complex internal structure that resembles a layered cocktail made of the most exotic materials in the universe. Some layers might be pure liquid diamond, while others could be mixtures of diamond with other ultra-compressed materials like supersonic ice or metallic hydrogen. The boundaries between these layers become zones of extraordinary chemical activity. Where liquid diamond meets supersonic water, chemical reactions occur that have never been observed in any laboratory on Earth. These aren't the familiar chemical processes we study in textbooks. These are reactions between materials in states of matter that exist nowhere else, creating compounds and molecular structures that challenge our fundamental understanding of chemistry. These exotic chemical processes might explain one of the most puzzling aspects of ice giant evolution. Computer models of planetary formation suggest that Uranus and Neptune should have cooled down billions of years ago, becoming cold, dead worlds with no internal heat sources. Yet Neptune continues to radiate more energy than it receives from the Sun, while Uranus shows signs of internal thermal activity despite its apparently dormant state. The answer might lie in the slow, ongoing chemical evolution occurring within these diamond oceans. As different layers of exotic matter interact over geological timescales, they release energy through chemical processes that operate according to principles we're only beginning to understand. These reactions don't consume fuel in any conventional sense. Instead, they derive energy from the gradual reorganization of matter under extreme pressure, creating a form of planetary metabolism that can sustain itself for billions of years. This internal chemical evolution has profound implications for how these worlds might change over cosmic timescales. The diamond oceans within Uranus and Neptune aren't static. They're slowly evolving, with new layers forming and old ones transforming as the planet's internal pressures and temperatures shift over millions of centuries. Future observations might detect evidence of these internal transformations through subtle changes in the planet's magnetic fields or heat output. If we could monitor these worlds over thousands of years, we might witness sudden shifts in their atmospheric dynamics as internal chemical processes reorganize their heat transport systems. These would be planetary-scale chemical reactions, invisible from the outside but capable of completely transforming how these worlds interact with space around them. The implications extend to the moons orbiting these ice giants. The tidal forces that flex and heat these satellites are generated by gravitational interactions with planets whose internal structure is constantly evolving. As the diamond oceans within Uranus and Neptune slowly change their density distributions, the tidal heating experienced by their moons might intensify or diminish, creating cycles of geological activity that span millions of years. Triton's nitrogen geysers, those spectacular eruptions that shoot material miles above the moon's surface, might be powered by tidal heating that varies over geological time as Neptune's internal structure evolves. Periods of intense geological activity might alternate with dormant phases as the parent planet's internal chemistry shifts between different configurations. This long-term variability in tidal heating could create environments on these moons that cycle between frozen sterility and active geology over time scales that dwarf the evolution of life on Earth. Subsurface oceans might freeze solid for millions of years, then thaw and become active again as their parent planet's internal chemistry enters a new phase of evolution. The search for life in these environments becomes a question not just of whether conditions are right today, but whether they've been stable enough over geological time to allow complex chemistry to develop and evolve. The exotic chemical processes occurring within ice giant interiors might create cycles of habitability that operate on timescales far longer than anything we see in Earth's biosphere. Understanding these cycles requires us to think about astrobiology in entirely new ways. Life that might exist in the subsurface oceans of ice giant moons would have to adapt to environments that change dramatically over millions of years. Such life forms would need to survive periods of complete freezing, then rapidly adapt to renewed geological activity as their worlds thaw and become active again. The chemical diversity created by these cycling processes could drive evolution in directions we can barely imagine. Each freeze-thaw cycle might create new chemical environments, new energy sources, new challenges and opportunities for biological adaptation. Over billions of years, such environments might produce forms of life that are adapted not just to extreme conditions, but to extreme variability in those conditions. These possibilities transform our understanding of what constitutes a stable environment for life. Instead of looking for worlds with constant Earth-like conditions, we might need to search for environments that maintain their variability over geological time. The ice giant systems, with their slowly evolving internal chemistry and cycling tidal heating, might represent the most biologically productive environments in the outer solar system, precisely because they never remain static. The distances we discussed earlier, those billions of miles that separate us from these worlds, represent more than just physical space. They represent temporal distance as well. The processes we're describing operate on timescales that stretch from the formation of our solar system to its eventual death. The diamond oceans forming within these planets today will continue to evolve long after our sun has exhausted its nuclear fuel and begun its transformation into a red giant. In the far future, as the sun expands and Earth becomes uninhabitable, these ice giants might represent the only remaining outposts of complex chemistry in our solar system. Their internal heat sources, powered by exotic chemical processes and gravitational energy, could sustain active geology and potentially even life long after the inner planets have been sterilized by solar evolution. This perspective transforms these worlds from frozen wastelands at the edge of our solar system into potential refuges for complexity and life during the universe's far future. The extreme conditions that make them so hostile to current Earth-based life might be exactly what allows them to remain active and dynamic across cosmic timescales that encompass the entire evolution of stars and galaxies. The magnetic field anomalies we discussed earlier take on new significance when viewed through this temporal lens. The chaotic, multipolar magnetic fields of Uranus and Neptune might not be static features, but rather snapshots of planets whose internal structure is actively evolving. Over millions of years, we might see these magnetic fields reorganize completely as internal chemical processes reshape the conducting layers within these worlds. Such magnetic field reorganizations would have dramatic effects on the space environment around these planets. The radiation belts that trap charge particles would shift and change, potentially exposing their moons to completely different radiation environments over geological time. Moons that are currently shielded by their planet's magnetic field might become exposed to intense radiation, while others might become protected for the first time in billions of years. These shifting radiation environments add another layer of complexity to the potential for life in ice giant systems. Biological processes that might develop in the subsurface oceans of these moons would have to adapt not only to changing tidal heating, but also to varying levels of radiation as their parent planet's magnetic field evolves over time. The atmospheric dynamics of these worlds might also undergo dramatic long-term changes as their internal heat sources evolve. The 1,000-mile-per-hour winds we observe on Neptune today might represent just one phase in a cycle of atmospheric evolution that spans millions of years. Periods of extreme weather might alternate with relative calm, as internal chemical processes shift between different energy output modes. Understanding these long-term atmospheric cycles requires observations that span decades or centuries, pushing the boundaries of what's possible with current space mission planning. Future orbital missions to these worlds might need to operate for 50 years or more to detect the subtle changes that indicate underlying shifts in planetary evolution. The engineering challenges of such long-duration missions are staggering. Spacecraft would need to be designed to operate reliably for longer than the entire history of space exploration to date. Power systems, communication equipment, and scientific instruments would all need to function in the harsh radiation environment of the outer solar system for periods that exceed the working careers of the scientists who design them. But the scientific rewards would be unprecedented. Long-term monitoring of these worlds' evolution would provide insights into planetary processes that operate on timescales completely inaccessible through any other means. We would witness the slow chemical transformation of entire worlds, watching as diamond oceans evolve and magnetic fields reorganize over decades of continuous observation. The data from such missions would revolutionize our understanding not just of ice giants, but of planetary evolution throughout the universe. The processes occurring within Uranus and Neptune might be common features of ice giant planets around other stars, representing a class of world dynamics that we're only beginning to recognize in our own solar system. Current surveys of exoplanets suggest that ice giants might be among the most common types of planets in our galaxy. If the internal chemical processes we've been discussing are typical of such worlds, then the universe might be filled with planets undergoing slow, continuous transformation over billions of years. Each ice giant system might represent a unique experiment in exotic chemistry, creating environments and conditions that exist nowhere else. The implications for the search for life become staggering when we consider this possibility. Instead of a few potentially habitable worlds orbiting within their star's habitable zones, we might live in a galaxy where complex chemistry and potentially even life are common features of ice giant systems throughout the cosmos. The techniques we're developing to study the internal evolution of Uranus and Neptune will become essential tools for characterizing ice giant exoplanets. Detecting the subtle signatures of internal chemical processes across interstellar distances will require advances in observational technology that push far beyond current capabilities. Future space telescopes might be able to detect the thermal signatures of evolving diamond oceans within distant ice giants, or observe the changing magnetic field configurations that indicate internal chemical reorganization. Such observations would transform distant exoplanets from points of light into dynamic worlds, whose evolution we can study across cosmic time. The extreme distances and temperatures we've explored throughout this journey represent just the beginning of a story that encompasses the entire evolution of planetary systems. The ice giants floating in the cold darkness billions of miles from our sun are not just frozen relics of solar system formation. They are active, evolving worlds whose internal chemistry continues to unfold on timescales that span the history of the universe itself. As we push deeper into understanding these alien realms, we discover that the universe's capacity for complexity and transformation extends far beyond anything we encounter in our everyday experience. The diamond oceans, the supersonic ice, the cycling tidal heating, and the evolving magnetic fields all represent processes that operate according to physical laws we can understand, yet create environments so extreme they challenge our most basic assumptions about what's possible. The journey to comprehend these distant worlds has taken us from simple measurements of temperature and distance to contemplation of chemical processes that span geological ages. Each new insight into their nature reveals additional layers of complexity, additional mysteries that demand investigation additional wonders that expand our understanding of what it means to exist in a universe filled with worlds beyond imagination. These ice giants, in their perpetual dance around our distant sun, continue to teach us that the cosmos is far stranger, far more dynamic, and far more full of transformative processes than we ever dared to suspect. They remind us that even in the apparently empty reaches of space, incredible complexity unfolds on scales that dwarf human comprehension, creating environments where the very nature of matter and energy is continuously rewritten by forces we are only beginning to understand. The cold that would kill us instantly, the distances that stretch beyond our capacity to travel, the pressures that would crush our strongest materials, all combine to create worlds where the universe experiments with possibilities that exist nowhere else in our solar system. In studying these extreme environments, we learn not just about distant planets, but about the fundamental creative capacity of the cosmos itself to generate complexity, beauty, and wonder in the most unlikely places. The quest to reach these distant ice giants has pushed human engineering to its absolute limits, creating spacecraft that must survive journeys so long they outlast the careers of the people who built them. But the most mind-bending aspect of exploring these worlds isn't the technology required to get there. It's what we discover about the nature of time itself when we attempt to study them. Consider this carefully. When the Voyager 2 spacecraft transmitted its first close-up images of Neptune back to Earth in 1989, those radio signals had to travel for over 4 hours at the speed of light just to reach our planet. The images we received showed Neptune as it existed 4 hours in the past. But here's where it gets truly strange. By the time those signals reached Earth, Neptune had already moved thousands of miles along its orbit, spinning on its axis, generating new weather patterns, and continuing the complex dance of internal chemistry we've been exploring. This temporal displacement becomes even more extreme when we consider the light we see from these planets through telescopes. The sunlight reflecting off Uranus's methane-rich atmosphere left the planet nearly 3 hours ago. Neptune's distinctive deep blue color reaches our eyes carrying information that's over 4 hours old. We are literally seeing these worlds as they existed hours in the past, watching ancient light that began its journey to Earth, when these planets occupied completely different positions in space. But the temporal mysteries of these ice giants extend far beyond simple light travel time. The seasonal cycles on these worlds unfold over timescales that challenge our human understanding of weather and climate. Remember that Uranus orbits on its side, creating seasons that last 42 Earth years each. This means that right now, as you're listening to this, the northern hemisphere of Uranus is experiencing a summer that began before you were born and will continue long after many of us are gone. Imagine living on a world where summer vacation lasts for 4 decades, where an entire human generation grows up never seeing winter, where the atmospheric circulation patterns we observe today have been building momentum for longer than most people have been alive. The weather systems on Uranus aren't just meteorological phenomena, they're geological processes playing out in gaseous form across timescales that encompass entire human lifetimes. This extended seasonality creates atmospheric dynamics unlike anything in our solar system. As Uranus slowly tumbles through its 84-year orbit, different hemispheres gradually tilt toward and away from the sun, creating temperature gradients that shift with glacial slowness. The planet's atmosphere responds to these changes like a vast, slow-motion ocean, with circulation patterns that take decades to establish and decades more to dissipate. Current climate models suggest that Uranus might be approaching a particularly dramatic seasonal transition. Observations from the past few decades indicate that the planet's atmospheric activity has been increasing as its equatorial regions receive more direct sunlight. We might be witnessing the early stages of a global atmospheric reorganization that will unfold over the next several decades, a planetary-scale climate change driven not by any external influence, but by the natural progression of seasons on a world tilted on its side. The implications of this seasonal transition extend throughout the entire Uranian system. The moons orbiting this tilted giant experience their own complex seasonal cycles as their parent planet's orientation shifts relative to the Sun. These satellites alternate between periods of constant daylight and perpetual darkness, each phase lasting decades. During the long polar nights on Uranus's moons, temperatures drop to levels that freeze even nitrogen solid. Atmospheric gases that might exist in vapor form during the brief polar summers condense out of the thin atmospheres of these satellites, creating seasonal cycles of atmospheric collapse and renewal. Entire moon atmospheres might freeze out and fall to the surface during the decades-long winters, only to sublimate back into vapor when polar summer finally returns. These atmospheric cycles on the moons of Uranus represent some of the most extreme seasonal variations anywhere in our solar system. The temperature swings between polar summer and polar winter on these worlds exceed anything we see on Mars or any other planet with significant seasonal changes. We're talking about temperature differences of hundreds of degrees over timescales that span human generations. Neptune's seasonal story unfolds over even longer timescales. With an orbital period of 165 Earth years, this ice giant experiences seasons that last over 40 years each. But unlike Uranus, Neptune's axis isn't tilted to extreme angles, so its seasonal changes are driven more by orbital distance variations than by axial tilt effects. The most fascinating aspect of Neptune's seasons lies in how they interact with the planet's internal heat source. Remember that Neptune radiates 2.5 times more energy than it receives from the Sun. This internal heat creates a baseline temperature that remains relatively stable throughout the planet's long seasonal cycles. But the slight variations in solar heating as Neptune moves through its elliptical orbit create subtle changes in atmospheric dynamics that build up over decades. These gradual seasonal shifts on Neptune might explain the dramatic changes we've observed in the planet's weather systems. The Great Dark Spot that Voyager 2 photographed in 1989 had completely disappeared by the time the Hubble Space Telescope observed Neptune in the 1990s. New storm systems appeared in different locations, suggesting that Neptune's atmospheric dynamics undergo periodic reorganizations driven by long-term seasonal cycles. Current atmospheric models suggest that Neptune might experience predictable cycles of storm activity tied to its orbital position. Decades of relatively calm weather might alternate with periods of intense atmospheric upheaval as the planet's internal heat output interacts with changing levels of solar input. We might currently be witnessing just one phase in a cycle that spans multiple human centuries. The study of these extended seasonal cycles requires observational programs that span decades, pushing the boundaries of institutional memory and scientific continuity. The atmospheric changes we're trying to understand unfold so slowly that individual scientists might spend their entire careers observing just a fraction of a complete seasonal cycle on these distant worlds. This temporal challenge has led to the development of new approaches to long-term planetary monitoring. Rather than relying on individual missions or observational campaigns, astronomers are creating multi-generational research programs designed to track atmospheric changes over the decades or centuries required to understand these worlds' complete seasonal cycles. The data from these extended monitoring programs is already revealing patterns that were invisible in shorter observational campaigns. Subtle changes in atmospheric composition, wind speeds, and storm activity are beginning to show correlations with orbital position and seasonal timing. We're starting to see the first hints of how weather on these ice giants responds to seasonal forcing over time scales that dwarf terrestrial climate cycles. But perhaps the most profound implication of these extended seasonal cycles lies in what they reveal about the stability of planetary atmospheres over cosmic time. The fact that Neptune and Uranus maintain complex, dynamic atmospheric systems despite receiving so little energy from the Sun suggests that planetary atmospheres can remain active and evolving over billions of years. This atmospheric longevity has important implications for the search for life throughout the universe. Many of the exoplanets we've discovered orbit at distances from their stars, similar to Uranus and Neptune's distance from our Sun. If these distant exoplanets can maintain active atmospheric chemistry over geological timescales, they might provide stable environments for complex chemical processes to develop and evolve. The seasonal cycles we observe on our ice giants might be common features of planetary systems throughout the galaxy. Worlds with extended orbital periods and significant axial tilts could experience seasonal variations that span centuries or millennia, creating environments where atmospheric and chemical processes operate on timescales that allow for gradual complexity to emerge. Understanding how atmospheric systems respond to these extended seasonal forcing cycles becomes crucial for interpreting observations of distant ice giant exoplanets. The atmospheric compositions and dynamics we might detect on such worlds could vary dramatically depending on what phase of their extended seasonal cycles they're currently experiencing. Future space missions to study these seasonal cycles in our own ice giants face unprecedented challenges in mission design and operational planning. Spacecraft designed to monitor complete seasonal cycles on Uranus would need to operate reliably for over 80 years, while missions to study Neptune's full seasonal evolution would require operational lifespans exceeding human lifetimes. The engineering challenges of creating spacecraft that can function for such extended periods push far beyond current technological capabilities. Power systems, communication equipment, and scientific instruments would all need to be designed for operational lifespans that exceed anything currently envisioned in space exploration. But the potential scientific rewards justify these extreme engineering challenges. Complete observations of seasonal cycles on ice giants would provide insights into atmospheric physics and planetary climate dynamics that are impossible to obtain through any other means. We would witness the slow evolution of entire planetary weather systems, watching as global atmospheric patterns reorganize over decades of continuous observation. The data from such extended missions would revolutionize our understanding of planetary atmospheres throughout the universe. The seasonal processes we observe on our ice giants likely represent fundamental aspects of atmospheric behavior on similar worlds orbiting other stars. Understanding how these processes unfold over extended timescales would provide crucial insights for interpreting atmospheric observations of exoplanets. The temperature extremes we've explored throughout this journey take on new significance when viewed through the lens of seasonal cycles. The bone-chilling cold we've discussed isn't just a static condition on these worlds. It's part of dynamic thermal cycles that unfold over decades and centuries, creating environments where temperature changes occur so slowly, they're nearly imperceptible from a human perspective. During the decades-long winters on Uranus's poles, temperatures drop even below the already extreme baseline levels we've discussed. Atmospheric gases that remain in vapor formed during the brief polar summers condense and freeze, creating seasonal snowfalls of materials that exist only as gases at Earth temperatures. Methane snow, ammonia ice storms, and hydrogen sulfide frost represent just a few of the exotic weather phenomena that occur during the extended winters on these tilted worlds. The gradual transition between these extreme seasons creates atmospheric phenomena that have no analogue anywhere else in our solar system. As polar regions slowly warm during the decades-long transition from winter to summer, vast quantities of frozen gases sublimate back into vapor form. This seasonal atmospheric renewal drives circulation patterns and weather systems that build momentum over decades, creating global wind patterns that persist longer than human civilizations. These extended seasonal transitions reveal something profound about the nature of atmospheric dynamics on worlds with orbital characteristics unlike Earth's. The gradual changes in solar heating over decades or centuries allow atmospheric systems to reach equilibrium states that are impossible on planets with rapid seasonal cycles. The result is weather systems that achieve scales and intensities that dwarf anything possible on worlds with Earth-like seasonal timing. The winds we observe on Neptune, those 1,000-mile-per-hour jet streams that make hurricane-force winds seem gentle by comparison, might represent the culmination of seasonal atmospheric building processes that span multiple decades. These aren't temporary storm systems like hurricanes or typhoons. They're permanent features of planetary atmospheric circulation that develop and maintain themselves over timescales that encompass multiple human generations. Understanding how these long-term atmospheric processes operate requires us to think about weather and climate in entirely new ways. The familiar concepts of daily weather patterns and annual seasonal cycles become almost meaningless when applied to worlds where significant atmospheric changes unfold over decades or centuries. This temporal perspective transforms our understanding of what constitutes atmospheric stability. Rather than looking for worlds with Earth-like weather patterns that change rapidly in response to short-term forcing, we might need to search for planetary atmospheres that maintain their long-term circulation patterns over extended timescales. The ice giants, with their slowly evolving seasonal cycles and persistent atmospheric features, might represent the most stable atmospheric systems in our solar system, precisely because they change so slowly. The implications extend to questions about the potential for life in these extended seasonal environments. While the extreme cold makes surface life impossible by Earth standards, the slow, predictable nature of seasonal changes on these worlds might create subsurface environments that are more stable over geological time than anything we see on more rapidly changing planets. The subsurface oceans that might exist within the moons of these ice giants would experience seasonal forcing cycles that span decades or centuries, rather than rapid freeze-thaw cycles that could disrupt biological processes. These hidden seas might undergo gradual temperature and chemical changes that allow complex chemistry to develop and persist over extended periods. Such environments might favor the development of biological processes that operate on timescales completely unlike terrestrial life. Instead of rapid reproduction and adaptation cycles, life in these systems might evolve strategies based on extremely long-term stability and gradual adaptation to slowly changing conditions. The chemical processes that might support such life would derive energy from the gradual seasonal changes in temperature and pressure rather than from rapid metabolic cycles. These would be biological systems adapted not just to extreme conditions, but to extreme temporal stability in those conditions. As we continue to push the boundaries of our understanding of these ice giants and their extended seasonal cycles, we encounter phenomena that challenge our most basic assumptions about how planetary systems work. The distances that separate us from these worlds, those billions of miles we have explored, represent not just spatial separation, but temporal isolation from processes that unfold on scales that exceed human experience. Yet in studying these slow, majestic cycles of planetary evolution, we gain insights into the fundamental nature of how worlds change and develop over cosmic time. The ice giants, with their decades-long seasons and centuries-long orbital periods, serve as natural laboratories for studying planetary processes that operate on timescales that bridge the gap between human observation and geological evolution. The extreme cold and vast distances we've discussed throughout this journey represent just the most obvious characteristics of worlds whose true nature unfolds over timescales that challenge human comprehension. In learning to think about these ice giants as dynamic, evolving systems rather than static, frozen worlds, we begin to appreciate the profound complexity that characterizes planetary evolution throughout the universe. These distant worlds continue to teach us that the cosmos operates on scales of time and space that dwarf our everyday experience, creating environments and processes that reveal new aspects of physical reality with each new observation. The journey to understand these ice giants has taken us far beyond simple measurements of temperature and distance into contemplation of processes that span the entire history of our solar system and will continue long after our sun has exhausted its nuclear fuel. In the perpetual winter of the outer solar system, where sunlight arrives as little more than starlight and temperatures approach the absolute limits of cold, these ice giants continue their ancient dance around our distant sun, carrying within their frozen atmospheres and exotic interiors the keys to understanding planetary evolution on scales that encompass the birth and death of solar systems themselves. The quest to truly comprehend these ice giants reveals something that will fundamentally alter how you think about the very nature of planetary exploration itself. Because when we send our most sophisticated instruments across those impossible distances to study these worlds, we're not just gathering data about temperature and atmospheric composition. We're conducting experiments in time itself, watching processes unfold that began billions of years ago and will continue long after human civilization has transformed beyond recognition. Every measurement we take from these distant realms carries within it the accumulated history of our entire solar system. The exotic chemistry occurring deep within Neptune's interior today is driven by gravitational energy that was stored during the planet's formation over 4.5 billion years ago. The diamond oceans we've explored aren't just geological curiosities. They're active records of the violent processes that shaped our cosmic neighborhood when the sun was young and planets were still finding their final orbits. This temporal depth transforms every observation into a form of cosmic archaeology. When we measure the heat flow from Neptune's interior, we're detecting the echo of collisions between planetesimals that occurred when life on Earth consisted of nothing more than simple chemical reactions in primordial oceans. The magnetic field anomalies that puzzle us today might be fossil remnants of catastrophic impacts that tilted Uranus on its side during an era when our planet's atmosphere contained no oxygen. The implications become staggering when we consider what this means for understanding planetary evolution throughout the universe. The processes we observe in our ice giants today are simultaneously ancient and ongoing, representing a continuous transformation that connects the earliest days of solar system formation to the far future evolution of our cosmic neighborhood. But here's where the story takes an even more extraordinary turn. Recent theoretical work suggests that the internal evolution of these ice giants might not be a simple cooling process, but rather a complex chemical transformation that could fundamentally alter these worlds over geological timescales. The exotic materials we've discussed, the supersonic ice and liquid diamond oceans, might represent transitional phases in a much longer evolutionary process that will reshape these planets over billions of years. Computer models of ice giant evolution now suggest that the internal chemistry of these worlds operates according to cycles that span hundreds of millions of years. Deep within their interiors, layers of exotic matter might periodically reorganize themselves, creating episodes of intense chemical activity, followed by long periods of relative stability. These reorganization events could release enormous amounts of energy, temporarily increasing the planet's heat output and dramatically altering their atmospheric dynamics. If these models are correct, then the ice giants we observe today might be in just one phase of a much longer evolutionary cycle. Neptune's current high-energy output might not be a simple cooling process left over from formation, but rather evidence that the planet is currently undergoing one of these periodic internal reorganizations. Uranus's apparent thermal dormancy might indicate that it's in a different phase of the same cycle, with its internal heat temporarily locked away beneath layers of thermally insulating exotic matter. The possibility of cyclical planetary evolution on these timescales opens entirely new questions about the long-term fate of planetary systems. Rather than simply cooling and dying over billions of years, ice giants throughout the universe might undergo periodic episodes of renewed activity, creating complex evolutionary histories that span multiple phases of heating and cooling. These cyclical processes could have profound effects on any moons orbiting these worlds. The tidal heating that drives geological activity on satellites like Triton might vary dramatically as their parent planets cycle through different phases of internal evolution. Periods of intense tidal heating could alternate with episodes of thermal dormancy, creating complex geological histories on these moons that reflect the internal evolution of their parent planets. The subsurface oceans that might exist within ice giant moons would experience these cyclical changes as dramatic shifts in their thermal and chemical environment. Rather than simple gradual cooling, these hidden seas might undergo periodic episodes of intense heating, followed by long periods of stability. Such environments could drive chemical evolution in directions that are impossible in more thermally stable systems. The biological implications become mind-bending when we consider life forms that might adapt to these cyclical environments. Rather than evolving in response to relatively stable conditions, any life that develops in ice giant moon systems would need to survive dramatic changes in temperature, chemistry, and energy availability over timescales of millions or hundreds of millions of years. Such life forms would need to develop strategies for surviving not just extreme conditions, but extreme variability in those conditions over geological time. They might evolve dormancy mechanisms that allow them to survive the cold phases of planetary evolution cycles, then rapidly adapt to renewed activity when their environment becomes thermally active again. The chemical diversity created by these cyclical processes could drive evolution toward levels of complexity that are impossible in more stable environments. Each thermal cycle might create new chemical environments, new energy sources, and new evolutionary pressures, resulting in biological systems that are adapted not just to extreme conditions, but to extreme change itself. These possibilities transform our understanding of astrobiology from a search for Earth-like conditions to an exploration of life's potential adaptation to environments that change dramatically over cosmic timescales. The ice giant systems, with their cyclical internal evolution and complex tidal heating cycles, might represent some of the most biologically productive environments in our galaxy, precisely because they never allow life to become too comfortable in any single set of conditions. The distances we've explored throughout this journey, those billions of miles that separate us from these mysterious worlds, represent more than just physical space. They represent temporal horizons that stretch our understanding across scales that encompass the entire evolution of planetary systems. Every mile of that vast emptiness tells a story of gravitational interactions, chemical processes, and energy transport mechanisms that have been operating since the earliest days of our solar system. Current space missions face the challenge of studying processes that unfold over these extended timescales, with instruments designed to operate for decades at most. Future missions to the ice giants will need to be conceived not as single observational campaigns, but as multi-generational research programs designed to track planetary evolution over centuries or millennia. The engineering challenges are unprecedented. Spacecraft designed to monitor ice giant evolution over multiple cycles would need to operate reliably for longer than human civilization has existed. Power systems would need to function for thousands of years. Communication systems would need to maintain contact across interstellar distances as our solar system moves through its galactic orbit. Scientific instruments would need to remain calibrated and functional across timescales that encompass the rise and fall of entire human cultures. But perhaps the most profound challenge is conceptual rather than technological. Designing missions to study processes that unfold over such extended timescales requires us to think about scientific inquiry in ways that transcend individual human lifetimes, or even the persistence of particular human institutions. We would be committing our species to research programs that span dozens of human generations, creating scientific legacies that connect our current understanding to discoveries that won't be made until our great-great-grandchildren are elderly. The data from such extended missions would revolutionize our understanding of planetary evolution throughout the universe. We would witness the slow chemical transformation of entire worlds, watching as internal processes reshape planets over time scales that bridge the gap between formation and destruction. Such observations would provide crucial insights for understanding the long-term evolution of planetary systems around other stars. The techniques we develop for studying these extended evolutionary processes will become essential for characterizing the thousands of ice giant exoplanets we've discovered orbiting other stars. Many of these distant worlds likely undergo the same types of cyclical internal evolution we're beginning to understand in our own solar system. The ability to recognize and interpret the signatures of these processes across interstellar distances will transform our understanding of planetary diversity throughout the galaxy. Current exoplanet observations provide only snapshots of distant worlds at single moments in their evolutionary histories. But if we can learn to recognize the signatures of cyclical planetary evolution, we might be able to infer the complete evolutionary cycles of exoplanets from limited observational data. A distant ice giant that appears thermally active today might be in the middle of a reorganization event that occurs only once every 100 million years. The implications for the search for life become staggering when we consider the possibility that ice giant systems throughout the galaxy might be undergoing similar cyclical evolution. Rather than a few potentially habitable worlds orbiting within traditional habitable zones, we might live in a universe where complex chemistry and potentially even life are common features of ice giant systems that cycle through periods of activity and dormancy over cosmic timescales. The extreme temperatures and vast distances we've explored represent just the most obvious characteristics of planetary systems that operate according to principles we're only beginning to understand. The bone-chilling cold that would kill us instantly might be just one phase in thermal cycles that create temporary oases of warmth deep within ice giant moons over geological time. The impossible distances that separate us from these worlds might be crossed by chemical and energy processes that operate over millions of years, connecting different parts of these planetary systems in ways we're only starting to recognize. As we continue to push the boundaries of our exploration of these distant realms, we encounter phenomena that challenge our understanding of what it means for a world to be alive or dead, active or dormant, habitable or sterile. The ice giants, with their exotic internal chemistry and cyclical evolution, exist in states that transcend these simple categories, representing forms of planetary existence that are simultaneously ancient and dynamic, frozen and energetic, alien and fundamental to understanding how planets work throughout the universe. The journey to comprehend these worlds has taken us from simple observations of distant points of light to contemplation of processes that span the entire history of cosmic evolution. Each new insight into their nature reveals additional layers of complexity that extend our understanding of what's possible in planetary systems, while simultaneously highlighting how much we still don't know about the fundamental processes that shape worlds throughout the cosmos. These ice giants, floating in their perpetual winter at distances that challenge human comprehension, continue to serve as natural laboratories for studying the most extreme expressions of planetary evolution. They remind us that the universe's capacity for creating complex, dynamic systems extends far beyond the comfortable boundaries of our Earth-centered experience, reaching into realms where matter and energy interact according to principles that push the very limits of physical possibility. The cold that defines these worlds isn't just absence of heat. It's an active force that enables chemical processes and states of matter that exist nowhere else in our solar system. The distances that separate us from them aren't just empty space. They're the stage upon which gravitational forces and energy transport mechanisms operate over timescales that encompass the birth and evolution of entire stellar systems. In studying these extreme environments, we learn that the universe is far more creative, far more dynamic, and far more full of transformative processes than our everyday experience suggests. The ice giants stand as monuments to the cosmos's ability to create complexity and beauty in the most unlikely places, using the most extreme conditions to drive processes that reveal new aspects of physical reality with each new observation. The quest to understand what lies within these distant, frozen worlds has become a journey into the fundamental nature of planetary existence itself, revealing that even in the apparent emptiness of the outer solar system, incredible complexity continues to unfold on scales that dwarf human comprehension, creating environments where the universe experiments with possibilities that exist nowhere else in our cosmic neighborhood. As we stand at the threshold of truly understanding these mysterious ice giants, we encounter something that will forever change how you think about the very concept of exploration itself. Because the most profound discoveries about these distant worlds aren't coming from the data we collect about their current conditions, but from what that data reveals about the deep connections between planetary evolution and the fundamental forces that shaped our entire universe. The exotic chemistry occurring within these ice giants today carries the signature of processes that began during the earliest moments of solar system formation, when our cosmic neighborhood was a chaotic disk of dust and gas swirling around our newly formed sun. The diamond oceans and superionic ice we've explored aren't just geological curiosities frozen in time. They're active participants in an ongoing transformation that connects these worlds to the birth of stars, the formation of heavy elements in stellar cores, and the complex gravitational dance that determine the final architecture of our planetary system. This realization transforms every measurement we make from these distant realms into a form of cosmic detective work that spans billions of years of history. When we detect the unusual magnetic field configurations of these planets, we're not just observing current phenomena. We're seeing the fossilized remnants of gravitational interactions that occurred when the solar system was still young and chaotic, when planetary orbits were unstable and massive objects regularly collided with forces that could reshape entire worlds. The tilted orientation of Uranus, that strange characteristic that creates its decades-long seasons, might preserve evidence of the most violent collision in our solar system's history. Computer simulations suggest that knocking a planet completely on its side would require an impact with an object at least as massive as Earth, striking at precisely the right angle and velocity to impart the enormous angular momentum needed to flip an entire world. Such a collision would have released energy equivalent to millions of the largest volcanic eruptions in Earth's history, temporarily turning the Uranian system into a hellish environment of vaporized rock and superheated gas. The fact that Uranus and its moons survived such a catastrophic event and eventually settled into their current stable configuration represents one of the most remarkable examples of planetary resilience in our cosmic neighborhood. But here's what makes this collision story even more extraordinary. The impact that tilted Uranus didn't just change the planet's orientation. It likely disrupted the internal heat transport processes that keep Neptune warm today, explaining why Uranus radiates so little excess heat, despite being similar in composition and structure to its more distant cousin. The collision might have created a thermal short circuit within Uranus's interior, trapping heat deep within the planet where it can't escape to warm the atmosphere. So there you have it. The next time you step outside on the coldest day of winter and feel that bone-chilling air bite at your skin, remember that you've just experienced tropical warmth compared to the frozen hellscapes of Uranus and Neptune. These ice giants, floating in perpetual darkness billions of miles from our sun, represent some of the most extreme environments our universe has to offer, where diamond oceans flow beneath atmospheres so cold that the air itself would shatter like glass, and where the very concepts of distance and temperature are pushed to their absolute limits. They remind us that our cosmos is far stranger, far more wonderful, and far more full of impossible beauty than we ever dared imagine. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers!